All right, welcome back, everybody. I hope everybody's doing well. This is Chapter 8, video number 2, going over the second part of the chapter and up to the end. In today's video, we are going to be discussing voltage drop and opacity, table 31015B16, why the limitations on that table, right? Selecting conductor sizes. Then we're going to go over adjustment factor and correction factor, which are both forms of derating. Then we are going to talk about using the charts in the book. One of the unfortunate things that we're dealing with is that we're not in school, so we don't have the code books. I don't even have my code book, so I do have my phone code book app, but I'm not even worried about that because I want to make sure that you guys can get access to this information. So most of what we need is actually in your textbook, and I'll show you how to do that. The one thing that's not is this Chapter 9, Table 8. Going to be very important for the voltage drop. I'll explain how to use this, and we'll go from there. And then we have identifying conductors, all right, which will be through markings and through color coding. So we'll go over all that in the future, or in the near future. So with that said, the first thing we have up is voltage drop. So voltage drop is the loss of electrical pressure along a length of conductor caused by the resistance of the conductor. Resistance increases with longer wires, smaller diameter wires, and temperature increases of the wires. On installations of great length, the voltage drop may be so excessive that a larger diameter wire is needed to compensate. Okay, so that paragraph right there sums up voltage drop. Okay, so that's what you need to know about voltage drop. The biggest thing is that we've gone over that. What is voltage? Voltage is the pressure that pushes electrons through a circuit. So if we have a very long distance, it gets harder for that pressure to push it. So we have a loss in pressure, so voltage drop. Pretty simple. As the chapter goes on here, it's going to go into how to calculate. All right, and so I'm going to show you quick here. You have VD is equal to 2 times L times R times I. Well, 2 is 2, times L is our length, times R is the resistance of the conductor in ohms per 1,000 foot. All right, and that's that paper I was just showing you, NEC Chapter 9, Table 8. All right, and then lastly, I is I, all right, current in amps. Same thing we've always been using. So figure this one out. Let's start by looking at this piece of paper. All right, this fancy piece of paper that I have here is right out of the code book. It's Chapter 9, Table 8. If we look on here, it says Table 8 conductor properties, and it lists all sorts of stuff. The biggest thing is that we have our size American wire gauge and our KCMIL. Right, so we have our MCM and our American wire gauge, all numbered down the side. Okay, all the way up to 2,000, all the way at the bottom there. Oh, there it is. Okay, so you'll notice from 18 up to 6, we have 2 of every number: 18, 18, 16, 16, 14, 14, 12, 12, 10, 10, 8, 8, and then it's 1. Okay, the difference is that this is solid and stranded, and then this is only stranded. Okay, so if we look at this, remember one big way to find it is the area of the wire, or I'm sorry, the diameter, and the diameter of a stranded is slightly larger than that of a solid of the same size. So this diameter, all right, for 14 is 1.85. For solid is 1.63. Okay, I know that might be hard to see, but so that means that the top one is solid, the bottom one is stranded. The next big thing to look at on this is that most of the time we're going to be dealing with copper, all right, unless it says aluminum, but we're going to deal with copper, and there are 2 kinds of copper, which I will go over in a minute. We have uncoated and coated. Okay, so the uncoated is broken into 2 parts. I have ohms per 1,000 kilometer, and I have ohms per 1,000 feet. And then the coated is broken into 2 parts: ohms per 1,000 kilometer and ohms per 1,000 feet. All right, so I have the wire gauge, the size, and then I have the resistance in ohms per 1,000 feet on this side. As I said, coated and uncoated. I'll show you in the book in a minute in another chapter. Uncoated does not refer to insulation on the wire. Okay, uncoated refers to stuff that's been added to the. Well, you know what? Let's just go read it. Okay, let me find it. If I go to chapter 22. All right. Oh, there it is. Okay, so coated versus uncoated. When reading through the NEC, you may come across unfamiliar terms. It is not always easy finding out the meaning of such terms. For example, Table 8, Chapter 9 of the NEC has columns for coated and non-coated conductors. Coated conductors are wires that have been tinned or otherwise treated to prevent erosion or deterioration of a wire's insulation. Many conductors today using thermoplastic insulation are uncoated conductors, which are not tinned or coated in some other substance. When neither coated nor coated is specified, uncoated is usually implied. Coated and uncoated have nothing to do with a conductor being classified as bare, covered, or insulated. Those are entirely separate issues from coated and uncoated. An uncoated conductor can be bare, covered, or insulated. All right, so I hope that clears some stuff up with that. So now let me go back to where I was here. So looking at this, so ironically though, as I'm telling you now that we're going to pretty much go uncoated. Sorry. We're pretty much going to go uncoated. The first example that the book is going to show you is going to say it's coated. Just go with it. All right. So what I want to show you here, and you know, I'll maybe write one down. I don't know. In this case, hopefully you can see. It says, for example, the voltage drop of 50 feet of 10 American wire gauge coated copper conductors. See, there's that word, coated copper conductors carrying 30 amps would be. All right. So there's that formula that we just went over. So now it told us that it had a length of 50 feet. So I'm going to plug in 50 feet. And then it, oh, here's, okay, 1.26. So here's where we need that chart. So we're looking for a number 10 wire, and it's carrying 30 amps. So what we need is 10 wire. Okay, so there's my 10. All right, and unless specified, I would say go with the stranded. So I'll say with the bottom, and I'm going to come over. I'm going to come over, and that is uncoated. Nope. All right. Okay, so they're saying solid. So they're at 1.26. All right, I would usually go 1.29, but I guess it matters if it's solid or stranded. But anyway, in this case, it's solid, 1.26, because if we look right here, they have it in as 1.26. So they went solid. And then times 30 is the 30 amps. Okay? So to review that again, we had 2 times the length, which is 50, times 1.26, which we found on the chart, times 30, all right, for amperage. Okay, now we're going to do all that work. Have 50 feet of number 10 American wire gauge, coated copper. All right, so it's coated. And it's carrying 30 amps. So 30 amps. Okay, that's what I have so far. So that's what I have so far. So VD is equal to 2 times L times R times I. Okay, and then that whole thing is divided by 1,000. So just like when we did the reciprocal method stuff, I would write this stuff out if you're having trouble with it. It's going to make your life easier in the long run. So my length is 50 feet. So it's 2 times 50. All right. Times my resistance. Here I'm going to write 1.26 because that is the resistance value of the number 10 wire. 1.26, and then we're going to multiply that by our 30, and that we'll go here and we'll put it over 1,000. So now with all of that having been said, I'm going to go 2 times 50 times 1.26 times 30, all right, equals 3,780. All right, I'm going to divide that by the 1,000 that was here. I just brought it over, and that will now equal, divided by 1000 equals 3.78. So what this is telling us right here is that if I have a number 10 wire at 50 feet pushing 30 amps, I will have a voltage drop of 3.78 volts over that. So if I started, the book will go on to say this. Let me move over to this now. Thus, the actual voltage present at the device is 120 minus 3.78. Let me straighten that out. Or roughly 116.22 volts. Okay, so that's voltage drop. That's how much, 3.78 is how much voltage we lost. They're telling us the circuit is 120. This demonstrates how both the wire size, the cross-section, and wire length are important factors in determining voltage drop. I hope that was a good start for a voltage drop. We'll go over more of that as you guys see that you might need it.